Great.
So welcome everyone. I'd like to thank you for joining us for day one of the annual Mayor's Megawatt Challenge Forum. My name is Catherine Wilson. I am the manager of the Mayor's Megawatt Challenge, a program that's been working with municipalities since 2003 to reduce energy use in their own facilities. This is the 10th annual forum and the second online forum. And with this new online format, we're thrilled to welcome folks from across the country who no longer have the logistical constraints of attending in person. We're continuing with last year's theme of practical pathways to net zero carbon buildings. And today we'll be exploring the results of the roadmap to net zero ice rinks, a pilot which took a cohort approach to developing individual roadmaps for 9 municipal ice rinks from 7 municipalities to get their buildings to net zero carbon emissions over time. We'll share the best practices and lessons learned throughout the pilot so you can apply the learnings to your own portfolio of ice rinks. I'd like to take this opportunity to thank our sponsors, Simcoe Refrigeration and Enbridge Gas, who have been critical to helping us and our municipalities achieve our objectives. Next slide, please. So following the opening remarks, we'll dive right into the results of the pilot, followed by Amanda Martin from the City of Markham, who will speak to the experience from a participant perspective. David Fauser from Simcoe Refrigeration will then speak to refrigerants and how to consider the impact of refrigerants on climate. He'll also speak to the Net Zero Naturally initiative and share how their expertise can help you make informed and sustainable decisions about your ice rinks. And Emily Marleau from the Federation of Canadian Municipalities will then speak to the various funding options available for net zero arena feasibility studies and retrofits. Next slide. Concerning logistics, if you have any questions related to technology or non-content questions, please enter them into the chat box. If you have questions related to the content, please use the Q&A option. Depending on the nature of the questions, some will be addressed live in the Q&A and others in a session following each presentation. We'll also circulate a Q&A document after the event. And I would now like to turn it over to Jillian Henderson from Climate Challenge Network to provide the opening remarks.
Thanks very much, Catherine. Hi, everyone. I'm delighted to welcome you to our 2021 Mayor's Megawatt Challenge Forum. As Catherine said, I'm Jillian Henderson, Vice President of Programs and Partnerships for Climate Challenge Network, which includes the Mayor's Megawatt Challenge. From our team here today, in the background or presenting, we have Frank Camilleri, who's Vice President and Technical Lead on the Pathway to Net Zero Ice Rinks project, Ali Kassim and Avon Joseph, project engineers who both did a lot of the work, collecting data, walking the sites, analyzing the information and developing solutions, and Catherine, who introduced herself, who manages the MMC program. I wanted to take this moment while we're meeting on a virtual platform. We would like to begin by acknowledging the Indigenous peoples of all the lands we are on today, wherever we call home. We acknowledge the ancestral and unceded territory of the Inuit, Métis, and First Nations people. I acknowledge that I am speaking from the traditional land of the Huron-Wendat, the Haudenosaunee, the Anishinaabe, and the Mississaugas of the Credit River. This is an exciting event that we've been looking forward to for a long time. We get to talk about work that's been underway for more than a year, delayed quite a bit by COVID and other unexpected exciting events, with an amazing group of municipalities. These MMC members have been working with us to really understand what it will take in a practical way to get existing buildings to lower carbon emissions. It wasn't easy. It was a collective effort and a lot of work went into development from everyone involved. The municipal teams, which were quite numerous, depending on the municipality, it took a lot of people and a lot of coordination. Our fabulous technical advisory group, who provided a ton of important technical information that really pushed us forward, and our own team. This work is so timely and critical, as we are overwhelmed right now with stories of climate impact from COP26 and the devastation of the news from BC this week. It's daunting. There's a lot to do and not much time to do it in. But I have to commend all of you and everyone who's listening today for rolling up your sleeves and really digging into what it's going to take to reduce carbon emissions. I'm now going to hand this back to Catherine, who's going to provide some background on the Mayor's program and the pilot itself.
Thanks, Jillian. So just to give folks who don't know about Climate Challenge Network, just to give you a little bit of background. So Climate Challenge Network is a not-for-profit organization bringing together collaborative, data-driven sectoral programs focusing on building-related greenhouse gas emission reductions and energy and water efficiency, helping members future-proof and build resiliency in their organizations and communities. Climate Challenge Network also collaborates with industry and academic experts to share best practices and engage in real solutions to address climate change. So in a nutshell, building performance assessment starts with benchmarking. So we benchmark buildings against our database of similar buildings. For municipalities would include administration buildings, community centers, fire stations, the whole gamut of municipal building types. We take it a step further by breaking it down into energy use components, and targets are set based on the top quartile of the energy components. Of course, simple benchmarking doesn't work. We need to make real apple-to-apple comparisons, which is where adjustments come in. So we adjust targets for material things in the building that really make it different, including data centers, for example, and other energy intensive equipment. In the case of the ice rinks, things like numbers of ice pads, number of months of ice in, for example. So further information on the adjustments and the methodology, all of this is available in white papers on our website. Next slide. So two fundamental components of the Mayor's Megawatt Challenge program include our preoccupation with results supported by real data and the sharing of knowledge and best practices between the members. So there's 4 pillars: energy management, knowledge, peer networking, and recognition. So on the energy management side, we provide our members with energy savings and opportunity reports, which point to specific areas of opportunity for savings and can be shared with auditors, for example, who are tasked with finding the savings. Members also share the reports with their building managers and operators as a means to engage them, point to savings already achieved and additional areas of opportunity. We also provide tools such as a base electric mini audit, for example, that members use to pinpoint areas where energy use is high. Recognition is also a really important component of the program. It's been really useful for members for educating senior management and council and the public on the various initiatives. Awards are not being given out this year because of the uncertainty around building performance due to COVID-19 related building closures, but we will take that up again next year. And peer networking. This is a crucial component as well, mostly done through webinars, as a way for energy managers to connect with each other, as well as connecting with facility managers and operators. Next slide, please. So as mentioned in the agenda, here are today's speakers. We have Frank Camilleri from Enerlife, who will be speaking to the results of the pilot, Amanda Martin from the City of Markham, David Fowser from Simcoe Refrigeration, and Emily Marlowe from the Federation of Canadian Municipalities. Next slide, please. Thank you. So just to give a little bit of background, I'll go through this really quickly. Why did we undertake this pilot? With the pending climate crisis, municipalities across the country have declared climate emergencies. Associated with these declarations are greenhouse gas emission reduction targets, the most common being net zero emissions across all municipal buildings by 2050. So our member municipalities identified this as a priority for 2020 and beyond, and we responded. So next slide. So where did we start? Ice rinks were a great place to start, as 20 to 30% of a municipality's building portfolio energy use and greenhouse gas emissions are in arenas. So great area of opportunity and a priority building type. Next slide. Coming up with the best possible plans for the participating rinks was really a group effort, as Jillian mentioned. These are the technical experts, stakeholders, and sponsors who made it possible. So we were fortunate to have a technical committee made up of some of the leading experts in technology and ice rinks that volunteered hours of their time, lending their expertise to help shape the pilot and develop the measures. And of course, the Federation of Canadian Municipalities for supporting the initiative. Next slide. I'd also like to thank our participating municipalities for going on this journey with us. The City of Barrie, City of Brampton, Town of Caledon, Town of Halton Hills, Township of King, City of Markham, and the City of Toronto. Next slide. So many of you have seen this before, so I'll cover it pretty quickly. The roadmap follows a systematic process to identify 4 areas of the integrated solution for each arena. First, energy efficiency to improve operations and equipment efficiency, then heat recovery to put as much of the waste heat as possible back into the building, then integrating renewables to cover the remaining demand, and leaving purchased carbon credits and other offsets as the last resort. We've integrated the idea of zero over time because not everyone can get to net zero carbon immediately, especially with existing buildings. So this approach plans net zero improvements when equipment replacement or capital renewal is scheduled, while focusing on immediate savings from energy efficient operations. So getting an entire municipal portfolio to net zero emissions is achievable and financially feasible if it's done in stages, when systems are at end of life or capital renewal is necessary. So having a long-term plan in place using a staged approach and leveraging the replacement life cycle of existing equipment will allow for the planning of capital investment required to achieve net zero and assets to be replaced over time. Next slide. So here are some of the objectives of the pilot. So really to set carbon reduction targets for ice rink facilities, to determine a roadmap to achieving the targets in a financially sustainable manner, test the 4-phase approach that I just mentioned, and the net zero over time approach, build the case for low carbon measures by comparing business as usual with the best possible low carbon measures, introduce the integrated design process into measure development, compare ice rink performance metrics to evaluate ice rink building systems and identify opportunities for operational improvements and or better efficiency when replacing equipment, and support municipalities in planning equipment renewal in advance. So lots of objectives here. And the next slide. This shows the process, the overall pilot process. So starting with data collection and review, followed by site visits, measure review with the technical committee, as has been mentioned. And then key was integrated design workshops with the municipalities, which we'll explain in more detail on the slides to follow. And then workshops with the capital group, and then final reports. So all of this will be explained in more detail as we go along. And next slide. I'd now like to turn it over to Frank Camilleri to speak to the pilot.
Great, thanks, Catherine. Appreciate it. Yes, so yes, again, just reiterating and highlighting the challenging times we face today. This is a very important cohort project, and we're really happy to announce and the findings that net zero carbon emissions is achievable and is financially feasible in municipal ice rinks, point blank. So that's a big accomplishment. We're very happy with the results of this, and we'll go into more detail further down the slides. But it does require a more comprehensive evaluation of measures, looking at life cycle costing and accounting for total cost of ownership, like maintenance costs, timing of measures with capital renewal, and planned capital investments over time. Great, thank you. Next slide. Okay, so starting off with greenhouse gas emissions, sort of the big key aspects right now is that's really forcing us to focus on climate change here. So again, highlighting that quite considerable emission reductions were achieved with this study. We see them hovering around closer in the 90–95% range on average before having to resort to purchasing carbon offsets. So we think that ice rinks and the findings of this cohort project have come to a very a very promising outcome that target emission reductions can be quite significant if you look at things from a low carbon perspective. Want to quickly highlight a couple of sort of anomalies or items that sort of stand out. The 26% reduction in emissions. Just want to highlight that ice rink number 9 only considered operational measures. So it's good to highlight why that is lower than the rest of them. But just because in that specific rink, the life of the complex was there was some uncertainty associated past, say, 5 years. But it's good to know that just operationally, operational changes you can achieve, as much as 26% reduction in emissions. Again, just with that. So great accomplishment here. We're really happy that and we're a little bit surprised, I have to say, that you could achieve such large emission reductions without having to resort to purchasing carbon offsets. Next slide. So as Catherine mentioned earlier, the whole process, our ultimate goal is energy emission reductions, but it starts with energy efficiency improvements. And findings show here through the 9 ice rinks that were part of the participants in this, they actually can result in quite significant energy reductions as well. You'll see the range typically from 58% to 82%. I'll explain a little bit of this chart here because it's a bit of information. Maybe we can start off with ice rink number 3, Avon, just on the top there. So the first sort of bar, if you will, the blue is the existing 2019 electric energy use intensity. And then there's the thermal, the gas use intensity. Again, 2019 was chosen in sort of the pre-COVID year, something that's more typical. And once the roadmap findings and recommendations were taken into consideration, we end off with 7.8 equivalent kilowatt hours, and it's just electric only, and resulting in an overall energy use intensity reduction of 80.7%. So quite significant reduction. Again, keeping in mind that the approach for this, the taken was electrification, getting totally off of gas, or at least presenting options that would give the municipalities and the ability or a roadmap to get totally off of natural gas. You will see a range actually going up as high as 100% there. So you see ice rink number 7. That was a specific participant that wanted to avoid purchasing credits at all. So they wanted to have the building to be fully sustainable, have zero emissions without having to go and purchasing carbon offsets. I'd also like to highlight ice rink number 9, again, similar to the previous one, which is has a 35% reduction. Again, that's just operational in nature. So we're able to achieve just by operating optimization, operating low-cost measures, you can achieve a fairly significant reduction in EUI. As well. So we have a kind of a full gamut here, operational measures that get you a reduction in EUI of about 35%. And then you can get typically up to 80% or 82% without purchasing carbon offsets. And then if you can go to the full extent where one of the participants wanted to see what would be required to get you there. And really the solution for that was, and looking into more details, really is how much solar PV do I need to put in this place, or even using the car parking lot, if you will, the vehicle parking lot, to actually get down this low, and it's it's feasible. So again, just want to highlight that this is a wide range of different different ice rinks in different circumstances, just implementing just operational measures to getting fully off of the grid and being self-sufficient without any carbon emissions. Okay, next slide. So consistent with FCM, Federation of Canadian Municipalities approach and being supported and from that program, this cohort project, we looked at 3 scenarios here: the business as usual measure, the low carbon approach without funding, and we're fortunate enough to get some good information in the release of funding. Low carbon with funding that was actually released in April this year. So we decided to include that as part of the analysis as well. Next slide. So business as usual, just a little bit of background on that. So what we included for here were just standard replacements, like kind of like-for-like replacements with equivalent, no optimization of existing systems. So when we refer to operational improvements, none of that was incorporated here. No heat recovery was contemplated in this scenario, and nor were there any renewables contemplated. It's sort of the typical business as usual without considering any low carbon approaches, if you will, and high energy efficiency type measures. So next slide, please. The low carbon approach without funding. So essentially, the approach that was taken for this scenario was looking at maximizing energy efficiency, using heat recovery and replacement of equipment at end of life. So that was kind of the general approach that we took. We implemented or contemplated implementing operational measures first, again, consistent with the approach that Catherine highlighted in the four-phase approach. Make your building as efficient as it can be with the equipment that you have. And then also taking into consideration measures that are both technically and financially viable immediately. And things that come to mind are heat recovery, as well heat recovery on the refrigeration plant, as well as implementing a building automation system. So that's sort of the point that I'd like to make is that was the approach that we took with this low carbon approach. Again, without funding there, because it's self-sufficient without the funding that's available currently. Next slide. So the low carbon with funding is essentially the same approach taken as the low carbon without funding, except that we're taking into consideration the GICP funding that's available. Most of you are likely aware of that. I know that FCM. Many of you are aware of that very attractive funding that's available that funds up to 80% of the capital investments, but does require an accelerated implementation to end of March 2026. What this generally did was, in some cases, it accelerated the replacement of equipment before end of life. Typically, end of life equipment that may have been a few years out from 2026 was fast tracked in order to take advantage of this very attractive funding that's available currently. Great. Next slide. So sort of starting off with this and highlighting the findings, the low carbon approach or creation of a roadmap really requires the use of life cycle costing and net present value. So this is fundamental to the decision-making approach, and after working with all the participants, found that this is fairly well talked about, but not really used, and requires transformational change in the way decisions get made in the in capital replacement, equipment replacement, in order to get to net zero. Essentially, this is based on using net present value. Net present value takes into consideration sort of a long period of time, a 30-year life that we looked into, that would at least require the replacement of every piece of major equipment at least once, and it aligns well with the 2050 sort of ultimate goal that we're seeing being promised or being committed to by most nations across the world, and in Canada specifically, and becoming more and more aggressive as well. Life cycle costing considers the total cost of ownership, so not only just the initial upfront costs, but also operating costs such as utility, maintenance, and carbon taxes as well, and inflation and escalation rates as well. We'll get into a little bit more of that as well. And again, just a little bit more in that 30-year period. Again, it takes us really close to the 2050 period, where carbon emissions really needs to be at zero. And we're glad to see that Canada's working towards getting there sooner, sooner than later. So anyways, that's the approach of life cycle costing. We'll get into some of the results and share the results of using that present value measures from the slides that come. Next slide. So consistent with the Federation of Canadian Municipalities, the approach that's required or for their feasibility studies, we adopted that same approach, taking into consideration many factors. As I mentioned, life cycle costing is fairly comprehensive approach. It takes into consideration inflation, as you can see there, assumptions there. So this information was the best information we had available at the time of undergoing this, and so we take into consideration escalation rates in the different utilities, electric and gas being the major ones here. Escalation rates in labor and maintenance, discount rate, which is has to do with the time value of money, and again the amortization period of 30 years, which we talked about why we chose 30 years. Carbon pricing emissions, we referenced a document that had been published recently in the spring. Again, the most the most currently available information that we had while undergoing the analysis of this cohort project. Want to highlight the fact that carbon pricing is built into in reality is built into the utility rates, but it was very difficult and challenging to determine or get any forecasts from the utility companies regarding electric and gas and water rates that take into consideration carbon pricing. So what we did, as well as we did quite a bit of sensitivity analysis to the escalation rates, and concluded that even with the sensitivity analysis, the outcome really wasn't any different, although the financials changed a bit. The decisions that resulted from it didn't change, basically. So we just want to highlight that that's the approach we took in light of the difficulty of separating or or keeping the carbon pricing built into the utility rates. Okay, next slide. So this is this is an aggregate of all the findings from the cohort project. So we've broken it down by system type, and this is again an aggregate, an accumulation of all the ice rinks and the recommendations that were made for each one of them all together. So we present again the three options, the three different scenarios. So we look at the business as usual there, the low carbon approach without funding, and then the low carbon approach with funding. And we've prioritized them. We've listed them in order of absolute carbon emission reductions. So you can see the refrigeration plant measures have the biggest emission savings that, that from the cohort project, right? And so a good way to interpret this now, because we're getting into the life cycle costing and the decision-making process, is essentially the approach the life cycle costing took was relative to the cost in today's dollars with respect to the current state of the facility. So the business as usual, you'll see negative net present value because you'll be replacing equipment without any savings essentially associated with it. So that's why you'll see a negative cost there, a negative in net present value, because you're actually replacing equipment without any savings to offset that cost. Okay, so moving on to the low carbon approach without funding, you'll see that even though the initial outlay of costs is higher than the business as usual, the 11 million versus the 5.2 or 5.3 million dollars, you spend a little bit more money, but because there are savings along the way, then the net present value, the cost relative in today's dollars for proceeding with these low carbon measures on the refrigeration plant is positive, basically savings of $4.6 million versus the current operation today. So the financial attractiveness of the refrigeration plant low carbon approach is really $4.6 million plus $5 million. So it's $9 million more attractive financially to go and proceed with the low carbon approach, again, without funding. So we are fortunate to have funding at our availability that's available currently, and that is sort of the next column, which reduces the initial outlay significantly from $11 million to $4.5 million, and now the net present value is close to $15 million. So again, just an interpretation of that is it's $15 million plus the $5 million. It is favorable, close to $20 million more favorable in today's dollars than the business as usual scenario. Okay, and that methodology and that interpretation is how you interpret all of these measures. But again, as we started off, refrigeration plant measures have the largest impact on emissions, and has quite substantially, as I indicated earlier, quite substantial savings over the business as usual case. Okay, so again, just we'll talk about more details of each individual sort of system measures as we go on further in the presentation. But again, just wanted to highlight those items over there. There are a couple of items that stand out. That one there in particular, heating. So heating, you'll see that the NPV with the low carbon approach without funding is negative. However, the interpretation is that it is less negative than the business as usual, which means that it is more financially attractive to proceed with the low carbon approach than the business as usual. In fact, what it is, the interpretation would be is that it's approximately $2 million more financially attractive to proceed with that. So essentially it's 2.244 less the $214,000. So it's approximately just over $2 million more attractive to do so, to proceed with this. And then again, if you take advantage of the funding that's available currently, it is has a positive NPV in that case over there. Okay, so that's one area of focus that we want to bring your attention to. And then the enclosure piece there, you can see under the low carbon approach without funding, again, there is a negative net present values, which again, the interpretation is that relative to the current operation, there is a net cost to the facility. You'll see that the business as usual in this case here is $0. So financially, to do measures that are more enclosure related are not very financially feasible or financially attractive. I shouldn't say feasible, but financially attractive versus the business as usual case to get emission reductions. You do get emission reductions. As you can see, the enclosure does result in 90.8 tons of emissions savings, but it is at a cost over the business as usual. Okay. Okay, so a lot of information there. We'll get into a little bit more details, but if we can go to the next slide, that would be great. Okay, so this whole approach that we're talking about that we've highlighted from the beginning is really carbon reduction over time, trying to do so in a sustainable manner. So I'd just like to explain this graph a little bit. So this is over time, over the 30-year period that we examined from 2021 to 2051. The business as usual is the green line. So you can see that on the vertical axis, there's emission reductions. So the business as usual, for sake of simplicity, we assumed that, again, as business as usual, really not taking into consideration any emission reductions over the current systems that exist. Then there's the low carbon approach without funding, the darker blue line. So you can see that gradually over time, you get to quite a bit of a reduction from 400 to down to 45. You can see there 45.9 in 2036, and eventually down to zero in 2041 or close to 2041. It's 2.4 tons of CO2 emissions in 2041. Again, this is just a sample participant roadmap, if you will. The lighter blue is the low carbon with funding. Basically, as we mentioned earlier, because we're fortunate enough to have a fairly attractive funding mechanism available, the green and inclusive community buildings funding available that pays up to 80%. The recommendation that we made is we fast-tracked a bunch of the capital expenditure, so you can see that a lot of the carbon reductions happening a little bit early, because instead of waiting for end of life to replace the equipment, because you have this this incentive or this funding mechanism that again is very attractive, pays up to 80%. Fast tracking it by 2026, there's quite a bit of work that gets done, and you can see the carbon reductions accelerated quite considerably between the dark and the blue. Okay, great. Next slide. So what's very important based on conversations within municipalities is really just trying to understand cash flow. So the business as usual, showing the cash flow associated with this. You can see that the dark blue bars, if you will, those are outflows of cash, and those are generally based on end of life replacement of equipment, and it's again replacement with like for like. You can see that the cumulative cash flow, which takes into consideration operating costs as well, you'll see that there are no savings associated here. So the green bars don't exist over here because again, for simplicity's sake, the business as usual, albeit there might be some slight energy savings, but just with general, even like for like equipment, slight efficiency improvements in the grand scheme of things, it's negligible. But you can see here that the cumulative cash flow is negative over the 30-year period. I'd like to highlight maybe the next graph perhaps is a better one to highlight the different axes that we have over here. So just to explain why we even have the two different vertical axes here to better show the differences between cash flow and just inflow of cash in and out, right? So this is the low carbon approach without funding. Okay, so I'd like to explain the vertical one. So so this vertical axis here showing the cash in and cash out really makes reference to the $0 mark. There really is basically cash in and out. So anything in blue is a cash outflow. So that's an expenditure like a piece of equipment replacement or some work that's being done on the facility. Then the green bars are savings, be it savings because of a reduction in utility costs, carbon emissions, or you name it, relative to the current operation. So again, just to explain the left vertical axis, it's cash in and out, represented by bars. Green bars are savings, blue bars are outlay of cash. Now, you'll see on the right-hand side, there's cumulative cash flow. And this is quite a different picture than the business as usual. So again, highlighting the zero axis, if you will, the $0 axis on the cumulative cash flow, that's in yellow. And you can see the dotted line is really an accumulation of the cash flow throughout this whole low carbon approach without funding over the full 30-year cycle. So you can see on that red dotted line that initially, with expenditures coming out and savings coming in, you start seeing it initially bottoming out at 2022, and then starts to rise because you're getting some energy savings. And the point that's being where the cursor is, and that is right now, that's sort of the break-even point for the expenditures that happened up to that point. So 2031, 2032-ish time frame. Then it dips, it goes into a slightly positive situation and then dips back down again because there's a fairly large expenditure because of end of life equipment. Then you can see it goes back up again and it gets to a break-even point there as well as in 2038. Again, then another big capital expenditure and then another break-even point at 2044. But very important to see here that after 2043, the cumulative cash flow is very, very positive. It keeps increasing and it gets to as high as, I guess, near the end of 2050, 2051, close to the 12 or $13 million range right there. So again, relatively speaking, comparing and juxtaposing to the business as usual case where it stays negative pretty well through the whole 30 years, here the cumulative cash flow eventually gets to a fairly large positive number and never and only it dips up and down a little bit, but in the end, very, very positive impact on the cumulative cash flow. Okay, next slide. Again, this is just the low carbon approach, same as the previous graph, but with funding, so it just fast tracks things. So you can see a couple of key items that I'd like to highlight here is that the break-even point is sooner because you're only paying for 20%. The municipality is covered up to 80% of for funding from this GICB that's currently available. So you can see 2026 relative to the previous slide, which is closer to 2031. You can see also that on the cumulative cash flow, around the 2040 is the most negative it gets, and that's less than negative $2 million. So it doesn't ever really get below negative $2 million in terms of a cumulative cash flow. And then the break even is at 2041, 2042, and gets again as high as 14 or $15 million by the time you're through with this. Again, it just accelerates things. The break-even points, cash flow from a cash flow perspective, come in earlier, and it just makes it even that much more financially attractive. Again, a point here is that you don't need to have the funding to make it financially attractive. Low carbon, the low carbon approach is sustainable without the funding. This just makes it all that much more financially attractive. Next slide. Okay, so just a little bit more about the the wide range of different participating ice rinks. So again, there were nine ice rinks that formed part of this cohort project, but many of the ice rinks ranged quite considerably from one to the next. So we've got a good cross the spectrum of different types of rinks that out there that we think we've got a good cross section of what's out in the marketplace. So just I think a couple items that we wanted to highlight there is they varied quite a bit in terms of ice pad square footage. You can see that it goes as low as 15,000 on ice rink number 8. Right up until ice rink number 1 as high as 65,000. That becomes there's more ice pads, but generally the ice pads, even the size of the ice pads, varied a bit from one to another. A lot of the ice pad area differences come from the fact that they have more than one ice pad, or they have a combination of a curling rink slash ice rink pad. So again, just moving along on the columns there, pieces, the area that I like to focus on is the gross floor area. Gross floor area is ranged from quite a bit from ice rink number 9, around the 35,000 square foot range, which was mainly an ice rink with very little amenities. The main focus in that facility was just ice rinks, really, in a couple of meeting rooms and so forth. But when as high as in some cases, like ice rink number 1, 151,000 square feet, which included several ice pads, but not only several ice pads, but also many other amenities like fitness rooms and community rooms and so forth. So again, we got, I think, a fairly good cross section of different types of ice rinks that exist out there. Many with differing number of ice pads, as well as some facilities having quite a bit of areas other than ice rinks, right? So. And again, just continuing on there, the number of ice pads varied from 1 ice pad to as many as 4. One of them, I believe, included a curling rink. The months of ice in varied from 8 months to a year. And only just really wanted to highlight the fact that heat recovery only existed in a couple of locations. So in ice rink number 1 there, it included, even though there's 4 ice pads, there's 2 refrigeration plants, only one of the 2 refrigeration plants had the heat recovery. And ice rink number 4 had it. It was one of the more recent ones that was built in 2010. Again, just want to highlight that the remaining 7 did not have any form of heat recovery other than desuperheater. Desuperheater is sort of one of the more basic forms of heat recovery, but it is nominal, and it is only typically used for preheating domestic hot water. And even though many of them had it, not necessarily all of them were working. Okay, so just some general sort of characteristics of the wide range of ice characteristics that we had for the 9 participating ice rinks. Okay, next slide. Okay, as Catherine mentioned, what's fundamental to the Mayor's Megawatt Challenge program is in the approach that's used in that program is the use of metrics. Okay. So these metrics here, we looked at metrics of several components, starting off with compressors and brine pumps. This is very revealing. It reveals many different things here. First of all, that there's a wide range of design going on here. This is very consistent with this tendency for engineers to typically oversize. So again, just to put things in context and define what these metrics are. So it's compressors, watts of compressor power per square foot of ice pad. So to try to normalize it and make it more comparable, we normalize it based on ice pad. So not just square footage of the facility, which encompasses many other factors, but we try to normalize it, making it as comparable as possible. You can see on the compressor side, it varies anywhere from 4.7 right up to 9.49, 9.5. And, it's a factor of 2. And so, again, one thing to be mindful of is always questioning the metrics, the tendency of over-designing. And with over-designing, usually there's some inefficiencies associated with that. Same thing on the brine pumps as well. You get as low as 0.95 watts per square foot to 2.35. Now, there are some interesting aspects to this. So again, putting aside the over-design aspects, there are ways to help address this. One of them is to use the use of VFDs where it's possible. Compressors can be a little bit more challenging depending on the type of compressors, whether or not even a VFD can work on those. But for brine pumps, generally VFDs is one where we would strongly recommend the use of VFDs. Again, you need to be mindful. There's some technical aspects that you need to be mindful of. But also one of the other things that's interesting in the way that we use these metrics on the cohort project is the fact that there are many strategies that are being used, that especially being used in some of the facilities like ice rink number 9, for instance, which we mainly recommended only operational measures. They had already implemented many of the efficient operating strategies when it comes to the ice rink. And you can see with ice rink number 9 on the compressor side, the watts per square foot is 5.12. Again, indicative. Okay, it's on the lower end, likely explaining its efficiency, but also the fact that it can actually achieve the resetting that we're going to be talking about in some of the measures, where we're resetting the ice temperatures, where we're resetting the relative humidity, and this using the use of metrics is also helpful to to dismissing myths, if you will, that things can't happen because the equipment cannot get the ice back to temperature. For instance, we're seeing it in a lot of these. We're using these metrics to help explain why it's possible to do possible to implement these strategies. So again, I'll highlight ice rink number 9, which is very low on the metrics, both on the compressor side and the brine pumps, and they're able to achieve these fairly smart aggressive energy efficiency strategies without impacting the quality of ice and the ability to get the ice down to temperatures it needs to for that. Okay. So next slide. Just continuing on with other key equipment there. So dehumidifiers, again, similar approach here. We got some ice rinks that the metrics are quite low, 0.12, 0.22. And some of them, most of them have no issues achieving the set points that are required. But we want to highlight the ice rink number 7. It's a bit of an anomaly in that sense there, because it is a fairly large facility that is OHL, or it's part of that OHL circuit, a huge spectator area. So that's why you see it standing out, because it has it's the combining of dehumidification with ventilation requirements for the spectators. Now, again, just wanting to highlight that anomaly, but also give you some idea of how potentially oversizing could occur in the other rinks, right? So if you remove that anomaly, you can see the wide range of CFM per square foot of ice pad for these rinks, going from as low as 0.12 to 0.51, and the same thing on the fan side. Just showing that there's room for, there's definitely oversizing going on. And then those things need to be questioned every time especially end of life equipment. What is the right size I need? Don't oversize things. And how do you deal with it in the meantime while you're making the most use until you get to the end of life replacement? Same thing on the lighting pieces over there. You can see quite a bit of range of watts per square foot intensity. You see on the lower end the 0.23 and the 0.3. Most of those facilities have already converted most of their lighting to LED. But it's also important to say that even with this, again, this whole observation about just the natural tendency to over design to be safe exists everywhere, exists in the lighting as well. Many of these facilities that even rinks number 7 and 8 also have LED lighting. And again, you need to question, saying even the lighting, when you're converting to LED, does it make sure that it's done properly? There's oftentimes you can result in have intensities that are twice as much as another ones that achieve and still meet the same light level intensities as required by building code and yes, standards. So again, always question that. Always bring up and make use of the metrics to help make decisions when replacing equipment, when redesigning, to make sure that it is an optimal design, not extremely oversized. Okay, next slide. Okay, so this is total emission reductions by in absolute value. So ice rink number one is the sort of the biggest one. Had biggest absolute reduction of as much as 569 tons of reduction. You can see here again, ice rink 9 just pointing out that it was mainly operational recommendations that were made. It's you still get 30 tons there, but again, just highlighting the many different systems that exist in the facility and where most of the emission reduction lies. And you can see that refrigeration plant, the dark blue line that you see on the bottom, the first sort of bar, if you will, that is one of the more significant ones, followed by heating, typically. Again, just a bit of a cross spectrum of how each of the different facilities achieved reduction and the absolute magnitudes associated with each one of them. Okay, next slide. So this is on average the savings associated with system types, again consistent with the way we've listed them and by system type. So again, refrigeration plant on average in aggregate saved 29%. Was responsible for 29% of the emission reductions, followed by heating, which is 21%, and then getting down to resurfacing at 17%, and then followed with ventilation and humidification, and eventually down to lighting as well. But again, highlighting the big players over here, the big contributors to emission reductions, is really in the refrigeration plant, heating, and resurfacing. And we'll get into a little bit more details of the measures to follow. Anyways, just the types of measures that were being recommended and considered under these different categories. Okay, next. Sorry, next. Yeah, there you go. So again, just so those were a bit of sort of high level findings, if you will, in terms of the core project, the individual ice rinks, and we'll get more into the individual measures. But some of the key recommendations that we have after completing this cohort project is the importance of getting organized, gathering data and documentation. Again, we obviously had this the pandemic to deal with, which complicated things further. But again, which even emphasized more getting organized, how important getting organized is getting everyone involved. Why we feel this cohort project is turning out to be successful, as we're seeing hopefully many of these municipalities actually proceeding to implementation at this point in time. But it involved an integrated design process. Again, just following back and aligning back with the objectives is introducing this concept of integrated design process, getting everyone involved, getting the facility managers, getting the capital folks involved, getting the operators together and involved in the process, in the decision-making process along the way. So you get everyone gets an opportunity to voice their concerns and then so you can get buy-in at the end of it, and it's so that it does eventually get implemented. Again, the understanding life cycle costing throughout this. Again, we've had several discussions with municipalities. Many people were exposed to life cycle costing, but none of them were implementing it to the fullest extent, not to the extent in terms of using it to make decisions. And we're happy to hear that many of them were open and amenable to using that model, because that is the model that you need to really use when you're looking through the lens of trying to get to carbon zero, carbon neutrality, right? So some key things as well, I guess we stressed this a few times already, there's quite a bit that can be achieved with operational type measures. Implement them right away, because those are usually low cost, no cost type measures. Another really big sort of finding, if you will, really important to integrate the refrigeration plant with the other building systems. They were very much in silos. Refrigeration plant didn't commute much with the other building systems, and there's a need for that in order to take advantage of the heat recovery that that could be obtained from the refrigeration plant. Building automation system is essential. I mean, point blank, about half of the buildings had a formal complete building automation system. Some of them, the other half didn't. And again, that's a necessity these days, and can hardly implement operational savings, if you will, without that system, or at least you can't do it properly. And it's particularly heat recovery is part of that 4-phase approach that Catherine talked about, but is extremely important in ice rinks where there's a lot of heat recovery to be recovered. So again, these are the kind of the sort of six or seven main sort of recommendations that we have after having gone through this, the recommendations we have to municipalities going forward and trying to undergo this process. Next slide, a little bit more, I think, on the getting organized a bit more. So, so we understand that, there's a lot of there are a lot of existing buildings, and it can be a fairly overwhelming task, but there are a lot of things that can be done in the meantime that you can get started. Now, it's getting organized, I think. These are the areas that we would recommend that you immediately or as soon as possible, until, even if you may get to these buildings maybe 2 or 3 years out, is really start getting the buildings or getting the information ready that you need, and that'll be ready for performing the analysis on this. So the building performance data, getting monthly data, interval data, if available, the last couple of years is always very helpful and useful to doing the analysis that's required to creating a roadmap. Tracking the performance is very, very important. Critical to this is as part of the cohort project, the need for looking at the mechanical systems, the refrigeration systems is important. So assembling those drawings and having them readily available, so that when it comes time to do a more detailed roadmap, they're readily accessible. The setting up of BAS trend logs, that's extremely important. What we found in pretty well almost all the refrigeration plants that at least had a building automation system connected to it had good trend logs, but there was only about half of them that really did. And then the rest of the building, some of them had building automation systems there, but they had very few trend logs, and none of them were essentially really being monitored. So again, setting them up so that when it comes time to do a more detailed look at it, trends can be observed, and an analysis and can be done more thoroughly, and can be more representative of what is actually occurring there, as opposed to working on observations when you're doing a site visit or just general communication. Collection of previous energy audits and other measures that have been completed. Schedules, building condition assessments are very important. Having that all organized and ready, again, for quick access is important, because that forms part of the the capital plan over time. So looking at these building condition assessments and referencing when their end of life is, and planning it along the whole timeline horizon. And having your asset management plan, capital plan, updated as much as it can be, so it can be used and form part of the process in creating this roadmap. Okay, next slide. So to talk about this integrated design process, again, I mentioned it a bit beforehand. It's really getting everyone at the same table, getting the facility managers, building operators, the energy managers, asset management in there, including the financial folks, the building modeling modelers that we had, and then in conjunction with the technical advisory team, we had many players at the table throughout this whole process, and that's what makes it successful. Is you have everyone at the table here getting the expert advice that you can, and bringing them all together so that people can ask questions and get their perspectives heard, and get concerns addressed as soon as possible, so that they're heard, and that'll significantly improve the chances of success of making this roadmap work. That this roadmap just doesn't sit on a shelf; it's actually doable, and you get buy-in from all players there. So again, just highlighting this is a common theme in the program itself, and was successfully, we believe, successfully used at this cohort project. Next. So just again, identify, the continuous focus on just trying to do the operational low-cost measures first. So some of these items, optimizing ice temperatures, for instance, based on ORFA recommendations. So again, this is just a sample of a schedule that could be implemented, resetting the temperature up at night, up to 25, 26 degrees. Again, following standards from ORFA, and what we've seen actually some of the rinks actually accomplish, adjusting ice thickness where possible to closer to 1.25 inches. Again, you need to look at this with respect to your specific facility, adjustment of humidity set points, scheduling of buildings to operate just when needed, controlling light levels, making sure that you have the ability to do that based on the activity type, whether it's just a maintenance exercise or in between events, reducing the need for the water flooding. I guess it's so there's ways of optimizing the amount of water that is used during the flooding process. And in all of this, and especially in the operational pieces of it, operator training is critical. It's very easy to just make these recommendations and walk away. But what's needed in this is actually working closely with the operators, understanding what concerns may arise initially, and dealing with them as they come, so that the operators have support along the way to make sure that these measures that you're implementing get fine-tuned and end up being sustainable. So that's really, really important. Again, there were many of these ice rinks. It was very, we got quite a bit of pushback initially, but once again, this integrated workshops gave everyone the opportunity to bring up their concerns, and many of them were addressed. And I guess during the implementation, there'll still be this requirement to train and monitor and deal with any issues that come up. So again, just couldn't stress the operator training piece enough on this, and how important it is for the success of these roadmaps. Next slide. I mentioned several times, building automation is critical. These days, you need smart operations to make a building efficient. Again, just on some site visits, we had quite a bit of a mishmash of different types of systems that existed out there. Many of the buildings had a control system on the refrigeration plant. What was very challenging was remote access. So hopefully ironing that out, figuring out how to get remote access early on in the game is important. Wanted to highlight that none of the systems were really integrated the refrigeration plant with the building HVAC system. So again, they kind of operated more in silos. And many of the facilities didn't have a building automation system for the rest of the facility. So some key observations, and the importance of getting the BAS into these systems as soon as possible. Again, the strategies needed optimization. We realized that even those buildings that did have BAS, they weren't optimized, and that's very, very common. Not fully taking advantage of the occupied and unoccupied smart strategies. Definitely opportunity for improvement. And again, the need for setting up trend logs in archiving. We found that the systems that had a good refrigeration control system, they had some good trend logs, but many of them didn't. And so we recommend, again, kind of repeating myself, but we're recommending setting up these trend logs and making sure that they're archived, so for future reference, right? So next slide. So a little bit more detail on the building automation system. Of the 8 of the 9 rinks in the pilot did not have BAS systems that covered the whole building pretty well. Again, as mentioning, there's only, I think, one building that really had, I think, a comprehensive system that served both the plant as well as the refrigeration plant, as well as the rest of the building. Again, most of them had the capability of capturing trends from the refrigeration plant, but about half of them really didn't. Trends was difficult. It was just very difficult to get, many of which required actually physical visits to the site to get, because remote access was a problem. Anyways, it was a bit challenging to get trends, and many of the trends weren't even set up. And if they were set up, they weren't being looked at. Right. So again, implementing really important coming out of this to the importance of having a whole building BAS early on in this whole low carbon plan will really help get you on your way to achieving low carbon or zero carbon solutions into these ice rinks. Next slide. Just a sample of what you can do once you have the trends. This is just one sample facility where we looked at the trend logs available. We were fortunate to have one plant that was quite a bit of automation and quite a points being monitored. We actually could relate the refrigeration plant kilowatts to the occupied periods and unoccupied periods and the relative humidity set points. So during occupancy, again, we just the green graphs, they're showing average relative humidity, and the dark sort of square box is showing you the KW. I think what's important to note, just in this specific situation, and how important the trend logs can serve to be, is on the right hand side. You'll see that with a high relative humidity set point, focus on the 63.3% relative humidity and the 70.5 kW. You'll see that that is at that higher setting, the plant uses a fairly low refrigeration plant, which is why we recommend resetting the relative humidity in this space, at least in this specific facility, a little bit higher during unoccupied periods. Okay, again, this is just a sample of what you can do with the trends, but there's many things that you can do with the trends once you have that information, and the data doesn't lie, right? So it tells you and the importance of what is actually happening and the which is actually happening, and the importance of monitoring afterwards after you make changes to make sure that you achieve the outcomes that are desired. Next slide. So high impact measures. Again, just want to highlight, I know we broke them up into categories, but again, just highlighting it again, heat recovery is by far the biggest component here. Huge emission reductions in terms of absolute amount of tons of reduction in this core project, and responsible for 34% of the average emission reductions in each of the facilities once you've implemented heat recovery. We're replacing the gas boiler with electric is also another significant one there, and that one there we'll get into a little bit more. Replacement of ice, the ice resurfacing machine also has impact, but building automation system is also really critical because it's responsible for the smart operations. Then it gets down to other things like cold water system resurfacing, as well as a bit of solar PV. But again, highlighting the big players over here, and that is heat recovery and conversion to electrification, anyways. And so those are the big. Again, we'll get into a little bit more of the details of the measures here, and kind of want to get to those really quickly because I know we're running out of time. So again, refrigeration plant key measures, adding heat recovery, it's essential. You're throwing most of the heat. Currently, most of the facilities just throw the heat, discard the heat outside the facility, and when it can be used within the facility. The biggest barrier in the past has been being able to find the right temperature quality, if you will, to be able to use it in there. But there are heat recovery chillers, high temperature heat recovery chillers available today, or heat pumps to elevate the temperatures that come from the refrigeration plant, so they can be used fully being used with the existing building infrastructure. There's a need for adding ice storage to address misalignment of ice plant operations. So when we're talking about, a good example is when we're resetting or recommending that you reset the ice temperature at night, well, the refrigeration plant is not operating at that time. If you implement that strategy, well, but that's when you need heat. So basically, the use of ice storage will allow the ice plant to operate, produce ice, and make use of the heat, and then use that ice through the daytime. So again, there's an importance to use the ice storage there. Again, use of VFDs on burn pumps and compressors, which we talked about in the metrics, and optimizing strategies, optimizing the sequences of operation are really key fundamental measures that were included in the refrigeration plant. Next slide. On the heating side, again, sort of the number two, if you will, one in terms of impact on emissions. Optimization is key. Again, it's essential that a BAS really be used to control the boiler plant, most of which didn't have one. And then it's making sure that even when you put on a BAS, that smart operating strategies are used, and things like implementing unoccupied temperature setback, as also staging and so forth, to really optimize that operation, make it as efficient as it can be. A couple of the other key measures that fall in this category are really replacing spectator gas-fired infrared heaters. Most of the Rinks, probably, I think about 6 or 7 of them, had gas-fired infrared heaters, and the recommendation again is towards getting them totally off of gases to replace them with the electric equivalent. Boiler plant replacement with electrical equivalent. Again, that final sort of milestone is to get them totally off of gas, but must ensure that before you do this, the heat recovery is installed, so that all the electric boiler or electric heating equivalent is doing is just top up. You want to do that after the heat recovery is installed, so that you avoid this huge increase in utility costs. At least that's the way it was modeled, and that's what we're recommending going forward. One of the key aspects, this is a very sensitive issue, will be one that will be an ongoing thing during this journey to low carbon, is really understanding the electrical service needs of your facility. So electric equivalent boilers, if you will have a fairly large impact on the service, and in many cases it might require an upgrade, and those can be significant costs. So just something to be mindful of, right? Okay, good. Yes, resurfacing again. Key measure as well, reducing ice, resurfacing water temperature using cold water ice resurfacing technology, such as real ice or equivalent. That has a fairly large impact on emission reductions. We talked about this, optimizing the ice thickness where possible, according to ORFA standards, getting it down to closer to 1.25 where possible. And in the end, replacing the ice resurfacing machine, many of which are currently propane or gas-fired, natural gas-fired, with electrical equivalents at end of life. Okay, next slide. Ventilation, again, always talking about optimizing the existing equipment, BS control, optimizing the sequence of operation. Again, just some examples of the types of smart strategies that exist. And then when it comes time to replace the equipment, make sure you replace the existing air handling rooftop unit with equipment that has hydronic coils that are fed from the heat recovered from the refrigeration plant. Again, making use of the heat that you recovered from the refrigeration plant. Next. Dehumidification, some of the key, again, operational measures is really the ability to resetting and using a dew point control. So during unoccupied periods, you can increase that a little bit. Again, being mindful that you don't create any harm to the building structure. You don't want any condensation occurring, but definitely shutting off the outside air. And in many cases, you can shut off the dehumidifiers during this time, and only calling them back up again when and if the RH rises above it. But we found that if you shut off the outside air portion of the dehumidifier during this time, there's very little need or very little occasion for the RH to rise in the facility. Also, lower occupied set points. Set points during so to ensure that fogging doesn't occur and develop ice quality is not compromised. So basically, increasing the RH to a point where it doesn't create any issues. Leveraging outside air, again, this is more like economizer thing to help out where it can, to help dehumidify where possible, using enthalpy control. Consider retrofitting. We found a few in some situations where they had existing dehumidifiers that use gas-fired desiccant, that you could use heat recovery, or higher temperature heat recovery from the refrigeration plant using a hydronic heating element. Again, trying to reduce the gas consumption for this dehumidification process. And then one of the bigger findings on the dehumidification side was really evaluating separating ventilation needs for the spectators from the dehumidifier itself, and replacing dehumidifier at the end of life with an electric powered sort of desiccant wheel. Using heat recovery as a source of generation from the refrigeration plant. So again, from the heat that you can recover from the refrigeration plant, if you can nowadays, the desiccants can work with lower temperatures than were required when initially gas-fired desiccant dehumidifiers came out. So you can do that, and can be achieved a lot with the high temperature heat recovery chillers that are available to recover the heat from the refrigeration plant. So again, some key items in the dehumidification measure category. Next, renewables. We looked at several renewables. Geothermal solar PV seemed to be the most suitable given the large roof area. Seemed to be the most financially attractable renewable for ice rinks. Again, just ice rinks only. This cohort project, just to stress, only had ice rinks. It did not have ice rinks with pools or anything of that nature. Geothermal was analyzed in great detail. Only it was not very economically viable given how much easier it is to access and more cost effective it is to get the heat recovered from the refrigeration plant. Solar wall, solar thermal were also evaluated, but deemed not to be very financially attractive. So again, bottom line on the ice rinks, the cohort project, solar PV seems to be the one that is most attractive, and something we recommend you look into in more detail. Go ahead. Next one. Envelope, as we talked about before, there are a few of these, but the low east ceiling is one that is very common in ice rinks. About half of them, I'd say about half of them had them. Just need to be mindful of potential obstructions and sprinklers. But most of the times this can be addressed, especially in community type rinks. We recommend working closely with fire department and the low-E ceiling provider. But most of the times it can be very economical to do so. Typically not very attractive and create some technical issues in professional rinks where they need to have access to the steel, to the infrastructure underneath, and where there's lots of requirement to put up posters and marketing materials like that. So maybe problematic, but for the most part, community type ice rinks, low-E ceilings do a great job of reducing emissions. Again, other than low-E ceilings, typically envelope measures are not the most financially attractive. Usually these measures are driven by occupant comfort more so than emission reductions. Again, wall envelope insulation improvement and windows fall into that category, and generally very costly to do. Again, just keep that in mind when you're evaluating. Doesn't mean that they don't make sense, but the majority of them didn't really make much sense financially. Not the best way to get your emission savings. There's better alternatives, if you will, to do so. Okay, next. Water, a few key items here. Again, reducing the water floods. We found many of the, not all of them, but many of the participants were using more water than is needed for flooding, and we can get them down to 150, and in some cases, I think some were getting it down closer to 100 US gallons per flood. The use of water efficient fixtures, low-flow toilets, and things of that nature would also be were also helpful. Most of them actually had them already. Just something to point out, and I think maybe the pandemic helped encourage that a little bit more too, especially the touchless fixtures, if you will. Sort of they start and stop. Just be mindful of those types of fixtures that they need to be constantly monitored, because they can actually use even more water if they're not maintained properly. And again, heat recovery, we talked about that. The fact that you're using heat recovery will in the facility, which will reduce the use of the cooling tower, and in turn reduces water usage in those open cells. So these are some of the key measures in the water category. Next slide. Lighting. So this is the last of the measures. Lighting and lighting controls. Many of the facilities were already converting from fluorescent to LED. Many of them also had lighting controls, but they were being used to varying degrees. But we recommended that they vary the light levels based on activity type and be consistent with that approach. Use of occupancy sensors. Many of the facilities already used occupancy sensors to control lighting and intermittent use of space, like change rooms and the washrooms, and just need to understand the secondary effects of lighting, energy reduction. So it's great on the ice load. On the ice, it reduces the load on that, but in sort of non-ice rink spaces that require heating during the heating season, it's actually a negative impact. You get emission increase actually because of that. So just being mindful of that. I think that's it. Next slide. Okay, good. This is over to you, Julie.
Thanks very much, Frank. In the interest of time, we're going to skip over this next section. This will be familiar to many of you on the line already, because this organizational piece is really critical and really important to reaching net zero emissions in these facilities. We will be revisiting this topic in 2022, and we will address this in more detail. So we're just going to skip over this organizational piece, but we will share this in the forum proceedings after. Next slide, even. And as well as the implementation, support, and scaling up piece. This was, these things were identified as very critical from the pilot participants. So this will be further explored through the program in 2022. So we'll keep everybody posted on that one. And we had reserved time for Q&A, but it looks like Ali's doing a great job of handling, answering all the questions that have come up. So we're going to skip over this section, but if you do have questions about what's already been presented or for the rest of the presentations, please enter them into the Q&A box and we will make sure they get answered by the end of the presentation.